I'm just going to go through and highlight a couple of really important things here that people forgot. So I'm assuming that this is equal to K1 times H1 and E is equal to K2 H2. So I'm assuming that you look at that statement that says, assume the flow is proportional to level, and you write and you read those words and you're like, oh, okay, this is the math that corresponds exactly to those words. Okay? A lot of you appear to have thought about this slightly differently. I was trying to transmit that very, very straightforwardly. You may assume that the valves in lines GH, J and L can manipulate those flows directly, and this is a common metaphor that we'll be using quite a lot in this subject, is this idea that this icon tells you that this is a manipulated variable. So you'll see me later, and like you'll see control engineers do this a lot, where even if there's not a flow, they'll draw a valve in there because there's this link between, like, a valve means that this is something I can manipulate. So I've seen valves on electrical currents. I've seen valves on like flow rates of like, or stirring rates or whatever, you know, like people like draw a valve there because they're trying to tell themselves this is something that I can manipulate from outside. Here again, I'm trying to say that you manipulate those flows directly. I will also say that I think a lot of the problem here is that in resolving ambiguity, so a lot of people are thinking, but listen, you haven't told me, like you haven't been clear. You haven't told me whether that is a constant mass flow rate or a constant volume flow rate. And if I don't know that, like I can't even start the question. Like I don't even know. You know, like if he didn't say mass or volume, so now like what can I even do? You make an assumption. In fact, make a simplifying assumption. If you're modeling in mass, assume I meant mass. If you're modeling in volume, assume I meant volume. Right? I give you perfect license to interpret ambiguous givens in the simpler way. I'm almost never trying to have you develop a super complicated model. Right? Then, of course, we've got the densities of the substances, and we've got all the mixing and so on. So my basic approach on this is quite straightforward. I'm going to do mass balances over all of these areas. Right? And I'm additionally going to do, so let's call this mass balance. And then additionally, I'm going to do a component balance over the tanks. Now, there is a little bit of leeway here. You are perfectly welcome to do a component balance over the junctions as well. But what you'll find is, like again, I'm going to just tell you the way that I think about the problem. I like, as I've mentioned before, I like to have many equations that are very short in my models, rather than a small number of equations that are very wide. So I bias away from early substitution, and I bias towards having like a reliable set of nomenclature. So when I solved this problem in Modelica, I had a fraction for every single stream. So I had a XA, XB, XC, all the way through to XL. And a lot of you are saying, but there isn't like different XLs. Like that's all just one thing called X3. Cool. That's fine. Okay, I don't mind if you do that. That was what many of the TAs did as well. That's not how I roll, but I'm not going to mark you down for not doing that. I like that symmetry of being able to write a mass balance, and that mass balance over there, that first mass balance, ends up working out like this. So I like the symmetry of writing this mass balance in this form, which is dm1 dt is equal to A plus B plus, A plus L minus D. And then the symmetry that I'm talking about is that the symmetric component balance works out like this. So in my mind, that makes this a lot easier to check, right? Because you're just checking for consistent, so you're not mixing things that you've also inferred out of like other specifications. So I've got one of those for every one of these. So I've got a red one and a blue one for every one of these. You can handle the edge specifications or these junction specifications in one of two ways. You can reason that all of these streams will have the same composition, or you can do a component balance. Unfortunately, you can't do both. So you can choose either. In the Modelica, I'll be releasing the solutions as well. That's another big benefit of not giving you an extension, is that you have more time to study the solution, right? But I'll be releasing the solution later today or probably tomorrow, parts of it today and parts of it tomorrow. But you'll see that in the Modelica version that I did, I chose the equality route, not the component balance route, but if you can do it either way. Okay, so we know now that we've got, how many balances are we up to? So we've got, let's say, how many unknowns do we have? We have each one of these, or how many symbols do we have? Each one of these things is a symbol. And so we can easily count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 streams. Okay? And this is how I like going about things, because when you're going fast, it's better to do as much as you can in your head, right? Because writing takes time, I get that. So I usually try and kind of get a good strategy in my head first before I really start writing things down. But I can see, okay, so there's 12 streams, right? And each of them has a flow and a composition. Okay, so that's 24 symbols. Okay, just those are the things that are in the streams themselves. Then I know that I've got the tank states. So the tank states are, I have a mass and a volume and a level and a composition in each of the tanks, right? So I know that there's going to be mass, level, composition, and what did I say? Mass, value, and volume in the tanks. Now, why do I have the volume in there? Because that's going to allow me to make the link between the geometry, right? So the link goes, I want to do a mass balance, which links through the volume, which links to the level. Why do I need the level? I know I need the level because I've already written down an equation that refers to the level. So that's where I'm thinking as well. I'm definitely going to have a level as well. So if I have all four of those things in each one of the tanks, I have, so for the 3 tanks, right, I've got a mass, a level, a height, a fraction, and a volume. And so that's 4, so that's another 12 symbols. Okay, so I'm up to 36 symbols. Now, I believe that that is, in terms of the additional symbols that are not parameters, because obviously the tank surface areas and the densities of the substances are parameters in the system. So I could add another three surface areas and 2 densities as parameters. I am okay with it if you substitute those in, but I really prefer that if you don't. Because here's the thing that you just have to know about me. I have no numeric memory. And so a lot of you, when you solve problems, you rely on numeric memory. So you would rely, for instance, to know, you rely on me to know that when you write 800, that was the density of substance Y. Okay, here is something that I will not be able to do. When you write 800, I won't recognize that as the density of substance Y. I just won't. I can't tell you why. It's like some people have name blindness, I have number blindness. So as I've mentioned before, and maybe it's just because like I've spent almost all of my career writing models in terms of symbols and not in terms of numbers. Even when I was your age, I wasn't writing down the numbers. I was doing stuff on my calculator because we were still allowed to use programmable calculators then, and so I'd solve the whole problem symbolically and then substitute in at the end. That's just how I did things. And so I haven't developed the skill that you take for granted, which is, oh, when I say 3, that's a magic number. He said 3 cubic meters per hour, or what? 3 cubic meters is what the tank volumes must be. So I know that's a 3, so because that is definitely the volume of tank. Like I will not remember that, and I will ask you in your paper, what is this? And you'll say, obviously that's the level of, like, that's the volume of tank 3. I was like, how would I know that? Okay, so just something you like to know about me. So, what does that mean? When you write down these things, I'd prefer that you include those as symbols in your models, right? So you've got row X, row Y, A1, A2, A3. So those are parameters in the system, and I would prefer that if you added those. And so those are another 5 symbols. And so our total number of symbols now is 41. Is that right? 12 plus 24 plus 5 is 41. Yes. Yes, well, good catch. So K1, K2. Cool. You wanted me to model how it is in papers, right? This is how it is in papers. You're definitely going to go around this loop a couple of times. Okay, so that's the symbols. Now I start writing down the equations. I think one big part of confusion is that a lot of people were like very confused when I say that you couldn't do a volume balance instead of a mass balance. It is counterintuitive to me. You would have gotten your marks in the test if you did it. If you had used the kind of meta specification that you can assume that these mixtures form an ideal mixture, the volume balance. But I want you to understand what that means. The mass balance does not reduce to a volume balance. That is a consequence of specifying ideal mixing. So it's kind of a different thing. I personally don't think that you really need to go there because it is straightforward enough to simply state the model in mass terms. And so when I modeled the system, I didn't use volume balances, I just used mass balances. So I did a mass balance over these red. So I have 6 mass balances. And I have 3 component balances. I have 2 H equals or F equals KH kind of things. Now notice how I'm counting here. I'm just kind of verifying for myself. I'm not taking the time to write down these balances, right? Because I'm just kind of doing a sketch for myself. You can do this on your book. If you're doing semester test 1, question 1, what I recommend is that you take the first page of your exam book and you use it for this kind of a rough model. You then turn the page where you have 2 nice blank pages face on face. You can do your model on the one side and your nomenclature and stuff on the other side and your degree of freedom analysis. That way you're not like paging around all the time. It also makes it really easy for me to check that everything is okay. I recommend that you use colors and highlighters just for my benefit. Like a happy grader is a lenient grader. So the easier it is for me to see what you're doing, the easier it is for you to get marks. So I've got these. What did that end up with 43 symbols. So now I need to, if I'm going to solve this, I need to get to my degrees of freedom specification, right? So I've got 6 of these, 3 of those, 5 of those. I've got all of these are actually specified, right? As those are parameters. And so we're gonna assume for the purposes of the simulation problem that those things are known. So these are 7 parameters. Is that true? 7 parameters. Then we have variously all of the specifications about equality on the right-hand side, all those component balances, okay? So I count being equal to x3, 1, 2, 3, 4, 5, 6, 7 component amounts that are equal to the amount, the composition coming out of tank 3. So you can probably write them something like x1 equals, and then it's like xf equals xg equals xh. Now, just a piece of advice as well, when you write things like this,
x3 is equal to
there you go. When you write equations like this where you have this kind of serial equals, those are 1, 2, 3, 4, 5, 6, 7 equations. Right? You've written it on one line, but that's 7 different, like if you had to write those out one after the other, the mental trick is you just count the equal signs, right? So you have as many equalities as you have equal signs in that equality. So there's 7 of them. Who's keeping a running track here? So we've got 43 symbols. How many equations do we have now? So that's 10, 18, 21. Is that 25? What other specifications do we have? So those are equations, right? So what we're running now, how many?
27.
So what's 27 minus, or what's 43 minus 27?
We've got 3 times 16.
Any more? Any more things that we know? Yes. Ah, yes. Now we come to the specifications, right? So I'm going to put that separate because we know that we're going to do input specifications. Okay. So we have how many input specifications do we have? We have A, B, and C are fully specified streams, which means that they count 2 things each, right? So we have a flow rate and a composition, right, for each one of those things. So we've got 2 there, 2 there, 2 there. We also have a specification, and now this is not a steady state specification, but what we have is a specification that says these things will be known. So all of these are also inputs. And because those things, so we effectively have flow rate specifications for all of those things. Okay, so we have 6 plus 4 specifications. So where are we sitting now? So we've got our parameters are specified, right? So we've got already that. Then we've got, so 6 plus 4 is 10. Let's do this over here. We've got 3 geometry. And then we've got a whole set of density relationships, right? So assuming that we're using these mass fractions, we know that the relationship between the mass in the tank and the volume in the tank is going to be determined by the density of the stuff in the tank. And under some assumptions, the easiest way to write those in my mind are that we have three things of the form V is equal to X times, so the amount of X in each tank is mx, m1x1 say, right? The volume of that stuff is mx divided by rho x. Does that make sense? And so that's kind of the volume rho x plus the amount of the other component is m times 1 minus x, right? We can take out the m. So that's another 3. So now I believe we are fully specified. Jackpot, okay? It hasn't taken me that long. It's taken me a while to go back and forth, but I want you to understand the process, right? The really important thing that I want you to realize is that I did not go through this and start the model from the top and just keep writing until I had finished, right? I started here, collecting the equations together to make sure that I had enough stuff and that I had taken all the effects into account that would allow me to actually write the full version of the model. Now it's a case of actually just writing down all of those equations. Does that make sense? So in the interest of time, I'm going to show you, because we've actually together now, well done team, everybody. Do you see how this works? I just want to like really make sure that you understand. The degree of freedom check isn't something that you do just at the end as an afterthought. It's the way that you know that you're done. Right? One of the kind of themes, I write myself a list of to-dos for every time we do the subject. I'm like, you know what I should put more focus on this year is the ability, the ways in which you can check yourself. So I want you to be able to check without having a solution. That's a very poor way of checking yourself, because it only works if the problem isn't worth solving. Because no problem that you can find the solution to is worth solving. If you're really interested in the solution, just get the solution and go on with your life, right? The interesting, worthwhile problems are the ones that you don't have solutions for. And for those, you can't check by comparing to the solution. You have to have other checks. So how are we checking? As we write these things down, as we make those assumptions. And I just want to walk you through how this solution works out. This is the Modelica version. Yes?
What if you put a hell of a lot of equations and accidentally put in the dependence equation?
That's an excellent question. Sorry. Alex asks, how do I know that I haven't maybe included a dependent equation? So for instance, if I did a mass balance, so the exact context would be something like, remember I said, oh, you can't do a component balance and specify equality on all of these nodes. How did I know that? And the answer is that, unfortunately, the math itself won't tell you. Just by itself, like if you just write down, there's no easy way to count dependency. In modeling systems like Modelica, once you actually start modeling it, that will tell you that there's a singularity in the equations. One of the big things that I would like to encourage you to do during the semester test is not to get too hung up on getting the right answer. I want you just to remind yourself how many times, anybody here who's ever gotten a, actually that's a bad question, but like think quietly in your head, right? How many times have you gotten 100% for a test? A full test, like a semester test or an exam? Okay, how many times? Of those times, how many times did you actually know that you got 100%? And an interesting thing that happens with programming, and I want to just I know that I don't have a lot of time, but I'm going to tell you this because it's an important realization. Most of you will never get full marks in a test for all the questions, right? And for most of you, this will not bother you, and you won't know until you get your results back. Why am I saying that? I'm not dissing you. I'm just saying that unfortunately when you write a program, it tells you immediately that it's not working. And so the response of most of you is to say, oh, it's not working. I don't have 100% yet, so I'm going to do it again, and I'm going to do it again. And I'm going to take this weekend, I'm going to take 20 hours, and I'm going to keep going until all those red lines are gone, until it works perfectly. That's when I'm finished. This is not how you do anything else in your entire course. Right? It's not how you do your tests. It's not how you do your exams. You do a best effort, you hand it in for grading, you get back the marks, you learn from your mistakes, and you move on with your life. Okay? This subject is not designed as one, but it can become a time sink because it includes programming, and it includes programming that allows you to know that you haven't done it right. The difference between getting that first cut in, which would get you 90% in a test, right? How many people have made a mistake here? Now you can put your hands up. How many people have made a mistake where afterwards you realize like it's a single character edit? There's like a comma missing, there's like a piece of punctuation missing, okay? Cool. How many marks would you expect to lose for such a trivial error in a test or exam? Like fraction-wise, if that was the only thing that you did wrong in like an entire test, you would expect to hit high 90s, right? You wouldn't expect to fail the test. You would blame me if I failed you because you had like a parenthesis missing, right? Give yourself the same credit. Right? Your job is not to write flawless programs. Your job is to learn how to write models. If you make one or two small mistakes, that's fine. It's much better to try lots of problems halfway than to spend a weekend like chasing that one semicolon or whatever. It's not an effective way to learn to just keep going until it's right. Now, I will be putting up these. I want to comment on a couple of things here because they are interesting and you haven't seen them before. You'll see the basic structure is very familiar. If you've gone through the Zogeny book, which is linked on ClickUp, you'll have seen the basic idea of this. This is why I love Modelica, because it just like removes all the weird stuff and like allows you to focus as much as possible on the model. You'll remember every one of these things is exactly what we wrote on the board. These are all the variables, right? So we've got all the mass flow rates, we've got all the mass fractions in all of the streams. We've got one of these for every one of the tanks. We have one of these for every one of the tanks, so that's all like per tank. We have this, and this is new and amazing. Here I am telling Modelica that these things are parameters. They won't change during the simulation. But you should calculate that from the initial conditions. So I'm not going to give it, but like just work that out from the initial conditions and then use those as parameters during the time-dependent simulation. This is new, I think, because the previous one didn't have initial equations. This is the section of my model that allows me to specify directly the initial steady state conditions. Well, it doesn't have to be steady state. Here I'm specifying steady state. So you can see I've encoded just one-to-one all the specs from the question, right? So I've said, okay, all the levels must be 1. These are the additional equations given in the initial equation specification, and I know that it's steady state, so that's where all these equations are coming from. Okay? These equations are added to the full set of specifications during initialization of the model when Modelica runs the model. And so it does a solve for the initial equations first. It then uses those parameters, and it will use these equations to find K1 and K2, as well as the initial values of all the flow rates that are specified later. I've got a direct specification of my input flow rate. So this if statement over here encodes exactly the wording of the question. So for times less than or equal to 0, the flow rate is 1. After that time, it is equal to 1.5. I've written it this way just because it allows me to specify it in terms of rho x. These are the specifications of the fractions in. Any of these you can do time dependent. Here are the input specifications, which are in terms of those flow rates that we work out in the initial section. And then these are just all the mass balances, right? So these are the mass balances over the tanks, the component balances over the tanks. Notice the symmetry, which allowed me to just copy and paste. So I could like write the mass balance, copy and paste, and then add x's in front of all of them. These are the equations for the junctions. These are the equality constraints for the fractions that come out. These are the fractions coming out of the tanks. This is the discharge equation, the geometry of the tank, and the mass to volume relationship. Also notice that I'm stating those equations just in the form that are most natural to me. So I'm not having to rework those in any kind of way. That is literally the entire version of the model. If you run this model, I have included a stop time here. Please just remember, just also note that I recommend that you use the IDA solver for this because the default solver DASL doesn't work properly on this problem, if I remember correctly, but give it a try. I had success with IDA.